Assalamualaikum everyone and a very good day to all. In this video, we will continue to learn about the fundamental laws that govern electric circuits, and it is the Kirchhoff's law, and we will also learn about the voltage dividers and series resistors and current dividers and parallel resistors. So this is the second part video for chapter 2. Here is the table of contents for you to navigate through this video. Ohm's law by itself is not sufficient or not enough to analyze circuits. However, when including Kirchhoff's two laws, which we will learn in this chapter, we have a sufficient and powerful set of tools for analyzing a large variety of electric circuits. Okay, Kirchhoff's law were first introduced in 1847 by the German physicist Gustav Robert Kirchhoff. These laws are known as Kirchhoff's current law and Kirchhoff's voltage law. The defining equation would tell us how the voltage and current within a circuit element are related, and it will also tell us how the voltages and currents in different branches are related. So they govern how elements within a circuit are related. Okay, Kirchhoff's first law is based on the law of conservation of charge, which requires that algebraic sum of charges within a system cannot change. Okay, KCL or Kirchhoff's current law states that the algebraic sum of currents entering a node or a closed boundary is 0. So mathematically, KCL implies that the summation of all current entering or leaving the node from all the branches connected to the node. By this law, currents entering a node may be regarded as positive, while currents leaving the node may be taken as negative. But it can be the other way around as well. So let's see this example here. We have I1 entering, I3 is also entering, and I4, whereas current I2 and I5 are leaving the node. So we put all the entering currents onto one side and leaving onto one side. So current entering equals to current leaving. So I1 plus I3 plus I4 equals to I2 plus I5. If you bring I2 to the other side, I2 and I5 to the other side, then you'll get equals to 0. So this is the algebraic sum of currents. Okay, so those that are entering will be positive and those are leaving will be considered as negative. So if you change it the other way around, meaning that if it's entering negative and leaving positive, you'll get the same result. So in general, we can say that the summation of all the current involved within the nodes will be equals to 0. Note that KCL also applies to a closed boundary. This may be regarded as a generalized case because a node may be regarded as a closed surface shrunk to a point. In 2 dimensions, a closed boundary is the same as a closed path. As you can see, it is illustrated in the circuit on the left here. The total current entering the closed surface is equal to the total current leaving the surface. So entering is I1 and I3 and leaving is I2 and I4. So they are equate in the equation as I1 plus I3 equals to I2 plus I4. A simple of application of KCL is combining current sources in parallel. The combined current is the algebraic sum of the current supplied by the individual sources. For example, the current sources shown in the circuit on the right, you can see that it can be combined at the figure bottom, and the combined or equivalent current source can be found by applying KCL to node A. So here you can see how it is. I1 is entering node A and I3 also is entering node A, and whereas I2 is leaving. So that's why I1 minus I2 plus I3. This is the equivalent. Okay, let's do an example together. Given that ascension node is the point within 3 or more branches, apply KCL to each ascension node in the circuit. So let's see. First, you have to identify where are the essential nodes. Okay, it needs to be at least between 3 or more branches. So in this case, let's start with on the left. Okay, can you find one? Okay, should be here. Okay, so this is your first essential node. So can you see what are the currents entering and what are the currents leaving? So current entering is I1 and current leaving is I6 and I8. So it should be I1 equals to I8 plus I6. Okay, so let's find another essential node. Again, it has to be between 3 or more branches, so I think it should be this one. Okay, so here we have 2 current entering and 1 current leaving. Let's start with the current leaving. Okay, so it doesn't matter which one you start first, as long as all the current leaving is onto one side of the summation mark, and also all current entering on the other. Okay, so it's an algebraic sum of current entering a node. Okay, so here we have I3 equals to I6 plus 5 milliampere. Okay, so where is the last essential node? Can you find it for me? Okay, I hope you can find it. Okay, so this is your final essential node in this circuit. So here you can see that there are 4 branches that are connected to this node, to this essential node. So you have I1 leaving, I8 entering, and then you have 5 milliampere leaving, and I3 entering as well. So let's do the equation, apply KCL. So it should be I1 plus 5 milliampere, which is current leaving, equals to I8 plus I3. Let's move on to Kirchhoff's second law. It is also known as Kirchhoff voltage law, and it is based on the principle of conservation of energy. So Kirchhoff voltage law, or KVL, states that the algebraic sum of all voltages around a closed path or loop is 0. If you notice that in KVL we deal with loop or mesh, and in KCL we are dealing with nodes. Okay, so we can express mathematically as this, where M is the number of voltages in the loop, or the number of branches in the loop, and V of M is the mth number of voltage. So to illustrate the KVL, we can consider this circuit. So the sign on each voltage is the polarity of the terminal encountered first as we travel around the loop. So we can start with any branch and we can go around the loop either clockwise or counterclockwise. Suppose we want to start with the voltage source here first and go clockwise around the loop as shown. Okay, so the voltages would be minus V1 plus V2 plus V3 minus V4 and plus V5 in that order. So for example, as we reach branch 3, the positive terminal is met first. Hence, we have positive or plus V3. And for branch 4, we reach the negative terminal first. Hence, we have minus V4. Thus, KVL yields minus V1 plus V2 plus V3 minus V4 plus V5 equals to 0. We can rearrange the terms, gives V2 plus V3 plus V5 equals to V1 plus V4. This can be interpreted as sum of voltage drops equals to sum of voltage rises. Okay, so this is an alternative form of KVL. Notice that if we had traveled counterclockwise, the result would have been plus V1 minus V5 plus V4 minus V3 and minus V2, which is the same as before except that the signs are reversed. Hence, the previous two equations remain the same. When voltage sources are connected in series, KVL can be applied to obtain the total voltage. The combined voltage is the algebraic sum of the voltages of the individual sources. For example, the voltage shown in the figure on the left, and we can see the combined or the equivalent voltage source on the right, and this is obtained by applying KVL. And the method as shown here, you can see that minus VAB as we go along. This is clockwise, minus VAB plus V1 plus V2 minus V3 equals to 0. And we can also rearrange it so that VAB equals to V1 plus V2 minus V3. Let's do another example together. So here we have a circuit and we want to apply KVL to each loop in the circuit. So as you can see, this is not, we are not talking about independent loop, or we are not talking about mesh loops. It can be other path within a loop. So instead of just independent path would be around 3 loops, but here we can have 6 loops. Okay, so let's go one by one. Okay, so this is loop 1, and the KVL is minus 10 plus minus V2 plus V8 equals to 0. So for loop 2, we will see that it is minus V8 minus V6 plus V1 equals to 0. And then we go to the next loop. It is minus V1 minus V3 and plus V4. Okay. Okay, where's the loop 4? It should be here. Okay, so minus 10 minus V2 minus V6 plus V1 equals to 0. And then we have loop 5. It is the whole loop, the whole circuit altogether, minus 10 minus V2 minus V6 minus V3 and plus V4. Okay, so we have another loop that hasn't been taken care of, which is the minus V8 and minus V6 minus V3 plus V4. So I hope you are clear about the loops and KVL. Okay, let's do another example together. Let's find I0 and V0 from this circuit. Okay, let's find them using KVL. So you have to identify your loop, okay, the direction of your loop. So in this case, we are going with clockwise. Okay, so we have to go through, we have to go around the loop. So we're going to see minus 12, and then we have this element. Okay, we have to multiply the current with the resistor to get the voltage, and then we have a dependent voltage here with 2V0, and then we meet with the negative terminal at 4 volts, and then we have minus V0, okay, and then equal to 0. Okay, so you have to be clear, you have to make sure that all the terms within this equation are all in terms of voltage. Okay, so that's why, especially for the second element here where we have 4 kilo ohm branch, you have to make sure that it is in terms of voltage, where V equals to IR. We already know I equals to I0 and R equals to 4 kilo ohms. So we just multiply them together to get the voltage term for this particular element. Okay, so what do we do next? Okay, from the circuit itself, you can see that, okay, the last element, the V0, you can see that it is equal to minus V0 equals to minus 6K multiplied with I0, okay, because the current I0 is entering through the negative terminal of the resistor, so it is minus 6K multiplied with I0. Okay, so from these two equations, we can find our answer by substituting. Okay, then after substituting, we'll get this equation, and from there on, we can get the answer right away because we only have two unknown variables and we have two equations. So I0 is minus 8 milliampere and V0 is just multiply, you just substitute, and then you can get the answer, 48 volt. Okay, let's do another example. This one is more complicated as compared to the simpler one just now. So in this case, we have two loops. Okay, we have loop 1 and loop 2. We need to identify the direction of the loop. So for loop 1, I'm saying it is clockwise, and for loop 2 is counterclockwise. So you need to find I7, I3, I2, V3, and V1. So we can use KCL and KVL in this case because whenever we have intersection of nodes, okay, then we definitely need to use KCL. Okay, so using KCL, at the node at the top, we can see that I3 is leaving and I2 and I7 is entering. So I3 equals to I7 plus I2. That will be our first equation. And yes, current leaving equals to current entering the node. And then we do KVL for loop 1 and loop 2, where we'll get minus 10 for loop 1, minus 10 plus 7k multiplied with I7 plus V3 equals to 0. This will become our equation 2, and then we have minus V1 plus 20k multiplied with I2 plus V3, okay, equals to 0. And this will be our equation 3. From as I go along, I can see that there is another equation that we can use. Okay, from the circuit itself, we can see that I2 equals to 5 milliampere. We can also then we can substitute this given information into equation 1, and now we can update the equation 1 becomes I7 equals to I3 minus 5 milliampere. Again, from the circuit, another thing that I can see that there is another information which is at V3, okay, there is a connection between 30k kilo ohms and the current flowing rate. So we have this equation, V equals to IR. Okay, V is V3, I is I3, and the R is 30 kilo ohms. Okay, so now we have 4 equations. Okay, so substitute I2 into equation 3 and we get this minus V1 plus 100 plus V3. Okay, so let's just update this into the third equation. Okay, and then substitute new equation 1 into equation 2 and you will get minus 360 plus 70k multiplied with I3 plus V3 equals to 0. Okay, so this become your new equation 2. Okay, of course there are different method, different flow of calculation you can do it. So it depends on how you think, I guess. Okay. So let's proceed to the next page. So again, using KCL, we can see that these are the equation that we've gotten just now, the updated one. Okay, so we have 4 equations. Okay, so using equations 2 and 4, we can get I3 and V3. Okay, so from there, you can right away get V1 and I7. So all the final answers are as given here. So you can check, you can do it from beginning until the end and see whether you get the same answers or not. So let's move on to resistors in series. Okay, the need to combine resistors in series or in parallel occurs so often that it requires special attention. Okay, so the process of combining the resistors is facilitated by combining them, two of them at a time. Okay, with this in mind, we can consider this single loop circuit. The two resistors are in series since the same current are flowing in both of them. Okay, so let's apply Ohm's law to each of the resistors. So we will obtain V1 equals to IR1 and V2 equals to IR2. If we apply KVL to the loop, in this case moving in the clockwise direction, we have minus V plus V1 plus V2 equals to 0. So if you combine the two equations, we'll get V equals to V1 plus V2 equals to I in the bracket R1 plus R2 equals to I R equivalent. So in this case, we can see that there is an equivalent resistance of the two resistors where R1 plus R2 equals to R equivalent. Okay, so from there, we can actually replace this circuit to another circuit, this circuit. Okay, so this implies that the two resistors can be replaced by an equivalent resistor, okay, which is called R equivalent. Okay, the figure previous circuit can be replaced with the equivalent circuit, and the two circuits are equivalent because they exhibit the same voltage current relationship at the terminal AB. Okay, so the equivalent circuit is useful in simplifying the analysis of a circuit. Just imagine if you have more than 10 branches or elements, then definitely it would be so much simple. Okay, so in general, the equivalent resistance of any number of resistors connected in series is the sum of the individual resistance. When we have resistors in series, then we would definitely be able to do voltage division. Okay, the voltage drop across any one resistor can be known from the voltage division. And the current through all the resistors is the same by using the Ohm's law. V equals to R. And when we apply this, if there are only two resistors in this case, then we can have V1 equals to R1 divided by R1 plus R2 multiply with V source. And then V2 equals to R2 divided by R1 plus R2 multiply with V source. Okay, so this is the principle of voltage division. Notice that the source voltage is divided among the resistors in direct proportion to their resistance. The larger the resistance, the larger the voltage drop. This is called the principle of voltage division, and the circuit in this figure is called a voltage divider. Okay, let's move to resistors in parallel. Okay, consider this circuit here where we have two resistors connected in parallel, and therefore they would have the same voltage across them. Okay, so if we have Ohm's law, then you can get this equation here, and applying KCL at the node A gives the total current I as I equals to I1 plus I2. Okay, from these two equations we can get equivalent resistance of the resistor in parallel. Thus the equivalent resistance of two parallel resistors is equal to the product of their resistance divided by their sum. Okay, as shown here at the bottom, but it must be emphasized that this only apply to two resistors in parallel. Okay, so in this case we have, given the total current I entering node A as shown in this circuit, how can we obtain current I1 and I2? Okay, so we know that the equivalent resistor has the same voltage, or V equals to I R equivalent equals to I R1 R2 divided by R1 plus R2. And with this equation, we can combine with the previous equation, which is I1 equals to V over R1 and I2 equals to V over R2. You can get the bottom two equations here, which this can be used in combination with the Ohm's law, like I mentioned just now. And we can use this to get the current through each resistor. Okay, so this equation will show that the total current I is shared by the resistors in inverse proportion to their resistance. This is known as the principle of current division. Okay, so in this figure or circuit here, this is known as a current divider. And notice that the larger current flows through the smaller resistance. Before I end this video, let's do another example together. Okay, let's find R equivalent for the circuit. To get R equivalent, we need to combine resistors in series and in parallel. So right away we can see that 6 ohm and the 3 ohms resistors are in parallel. So we can find the equivalent resistance using the equation I gave you just now, and we get 2 ohms. Okay, notice that I used the double line there. This symbol is used to indicate a parallel combination. Also, here we can also see that 1 ohm is in series with 5 ohm, hence the equivalent resistance is 6 ohm. We just add them together, and now we can see that it is slightly more simpler, right? So let's continue because there are a few other things that we can do here. Like 2 and 2 ohms there are in series, so we add them together. And now this 4 ohms is now in parallel with the 6 ohm resistor. So 4 in parallel with 6, you'll get 2.4 ohms. And finally, you can see that they are all in series, so you just add them up all together, so you get the R equivalent equals to 14.4. If you have any questions or comments, please let me know. Thank you and see you on the next video.